Hi, I am Mikko. In our wood material science research group, we are currently investigating the relationships between micromechanics and moisture adsorption of wood by employing long-wave thermal imaging or thermography. The impact of this fundamental research could one day lead to updates to the material models that are used to describe the behavior of wood. A better understanding of the wood-water relations could enable us to build more efficiently with wood. Building with wood is a sustainability action since the material functions as carbon storage. Specifically, I study the heat release of wood, which is subjected to a high relative humidity and a micromechanical load. When wood is subjected to high relative humidity, as in water vapor, it adsorbs this vapor on the surface, at the sorption sites on the surfaces of its polymeric structure, while a micromechanical load rearranges the cell wall spacing of the wood. The sorption sites are physicochemically active groups known as hydroxyl groups, while the polymers are the building blocks of wood that make up its cell walls. The water vapor adsorption leads to a heat release. The heat is released due to the formation of hydrogen bonds between the water molecules of the vapor and the hydroxyls of the polymers. Adsorption is followed by a slow diffusion into the cellular structure of the wood. This diffusion is a mass transfer process that causes the wood to swell and reduces the mechanical properties of the material. Practically speaking, water vapor will always propagate into native wood structures. In our research, we have discovered that when wood microveneers are pulled along their grain, while maintaining a constant displacement and close to a constant microtensile load under a relative humidity gradient, the wood releases more heat than an unloaded wood specimen would. You can see this effect in a graph I have plotted, where the blue line is a loaded wood specimen and the white line is an unloaded specimen. This finding corroborates that of the literature, and we speculate that the cell wall spacing and accessibility of wood polymer hydroxyl groups, such as those of the potentially breaking hemicellulose, are changing and increasing. These differences are due to the microtensile load primarily acting on the reinforcing cellulose, as the hydrogen bonds between the hydroxyls of the wood composite structure are broken and reformed. While the mechanism is hypothetical and our work is in progress, we are working on quantifying the heat absorption of wood in a non-equilibrium state. Thank you.